Hello, welcome to the course Electronic System Design. In earlier lectures, we were discussing about Ohm's law, and then we discussed something about Kirchhoff's law, which are the laws to solve electrical circuits. So, we can solve any circuit using Kirchhoff law, KVL and KCL we can apply to almost all the circuits. However, it is advantageous to develop certain shortcuts or some techniques apart from Kirchhoff's law, which we can apply on circuits and come up at the output much faster than the KVL and KCL. So, there are certain theorems which are developed, for example, the Thevenin theorem or Norton theorem. These theorems you can apply on electrical circuits, though these are also based on the KVL and KCL only, but based on some properties which we use in Thevenin's theorem, we can arrive at the output much faster than applying a KVL KCL. The same circuit where we are applying Thevenin or Norton or any other theorem, the same circuit can be solved using KVL and KCL. Those are universal laws, you can apply to them, but by applying Thevenin theorem we can solve the circuit much easily and much faster than KVL and KCL. So, today's lecture we are going to discuss some theorems. For example, we have superposition theorem, Thevenin theorem, Norton theorem. These are very basic theorems which we need to understand first before solving the complicated circuits or making a complete electronic system design. So, we are going to discuss some theorems. So, we have multiple techniques, those are all based on KVL and KCL only, which are used to analyze the circuits. So, various techniques this is important to note that they are all based on Kirchhoff's law only. Are used for the circuit analysis. Main techniques are superposition theorem, Thevenin theorem, Norton's theorem, and maximum power transfer theorem. Each of these techniques have some strength aimed at solving particular types of circuit problems. So, Each of these techniques have strength aimed at solving particular types of circuit problem. So these are some theorems which we use for analyzing the circuit. Let's discuss the superposition theorem first. So this theorem, assuming that we have all the linear circuit elements in our complete circuit, this theorem says if we have multiple sources of voltage or currents and we have all other linear components, so at any particular point in an element or at a node, the output coming from all the sources, the same output you can compute if you consider one source at a time. If we have, let's say, two voltage sources or two current sources in our circuit and we want to measure the voltage at the load, so the load voltage will be the algebraic sum of all the voltages which happen at the load if we consider one source at a time. Two voltage source, we consider only one voltage source, shorting all the voltage other voltage sources and open circuiting all other current sources. We take one at a time and compute the voltage at the load, and we take algebraic sum of all the voltages. So total voltage will be the sum of all those individual voltage. This is what the superposition theorem says. The limitation of this superposition theorem is the circuit elements, all components we are using in our circuit, that should be linear. So that is a fairly good assumption we have for Thevenin, for superposition theorem. So we can write, it helps us to analyze a linear circuit. So this is a condition for all these theorems. The network or the circuit element should be linear with more than one independent source. The output of a circuit is determined by summing the individual responses of each independent sources. It's however important to note here the idea of superposition rests on the linearity property. And it is the property of an element describing a linear relationship between cause and effect. So superposition theorem says the complete output or the final output is nothing but the sum of the outputs generated by individual voltage or current sources. So we have, let's say, one voltage source and one current source. So we can take one at a time. We take, let's say, voltage source as a actual source and shorting or opening all other sources. So other sources, current source. So we do it open circuit, we do not do it short circuit because the internal impedance of the current source is very high, let's say infinite. For an ideal current source it is infinite, so we open circuit the current source. The internal impedance of an ideal voltage source is 0, so we short circuit when we want to replace it with its equivalent resistance. So we do all voltage sources as short circuit and we do all current sources as open circuit. However, if we need to assume the internal resistance of voltage source as well, for example, all actual voltage sources has certain amount of resistance, series resistance we call it, or the source resistance. If the source resistance is also known, for example 5 ohm or 10 ohm, so when we replace the voltage source by its internal impedance, then we should not short circuit it, we should replace it by that 5 ohm or 10 ohm internal resistance. So this is how we solve the circuit. Once we make the circuit, then it's simple KVL, KCL we apply or some mesh analysis we do to solve the circuit. So this is what the superposition theorem says. Let's take one example to understand how we solve the superposition theorem based a numerical question. So let's take this circuit as an example, and we want to calculate current in 23 ohm resistor. So we have this circuit given here. If we notice, we have one voltage source here and we have this current source. So we want to calculate how much is the current flowing, let's say I, in this 23 ohm resistor. So if we notice, this voltage source will also be applying certain voltage here in this node, let's say node A, with respect to ground. Let's say this is the ground. So at node A, we have certain voltage that will also cause certain amount of current in 23 ohm, and this current source, this is also pumping some current into this node, let's say B, and some amount of that current will also go into this branch 23 ohm, causing some current. So we want to calculate how much will be the total current in this 23 ohm, so that we can solve using superposition theorem. So let's see the how we solve it. So first we take step 1. We take only voltage source at a time. So if we draw the earlier circuit with only voltage source, then it looks something like this. We have only voltage source here, and we open circuit this current source, so there is no current flowing into this branch, and only this branch is there, 23 ohm arm, and we can easily calculate how much will be the current into this. So we can calculate first the R equivalent, that will be 47 plus this 27 and this 23 will be in parallel, and this 4 ohm is already in series with 23. So 27 is in parallel with 4 plus 23. So 27, this is in parallel with 4 plus 23. This comes out as 60.5 ohm. This is the total resistance which is seen by this voltage source, 200 volt. So IT, the total current, will be 200 volt divided by 60.5. This will be 3.31 amp. So the total current in 23 ohm, let's say I tick, due to this voltage source will be the voltage divider rule, 27 divided by 54 into the current, which is 3.31 amp. This comes as 1.65 amp. So this is the current flowing only because of this voltage source. In the step 2, we take only the current source. So if we draw the circuit again, This is the current source, and we short circuit the voltage source because the internal impedance is 0. If we write the R equivalent, the total resistance, this is 4 ohm in series with 27 and 47. This is 21.15 ohm. So we can say in 23 ohm resistance, current I double tick will be 21.15 divided by 21.15 plus 23 into the current source, which is 20 amps. This comes out as 9.58 amp. So now we have these two circuits. One, we replace voltage source as a source, and the current source is replaced by open circuit. We calculate the current in 23 ohm is 1.65 amp because of this voltage source. In the second step, we consider the current source and short circuit the voltage source, and we calculate the current in 23 ohm is 9.58 ampere. So the total current in 23 ohm because of both of the sources will be the algebraic sum of these two currents, 1.65 amp plus 9.58, that comes out to be I total I in 23 ohm will be equal to 1.65 plus 9.58. That comes out 11.23 amp. So this is how we solve a superposition based theorem based question. So we solved where we have two sources. However, if you can have multiple sources altogether in all these circuits, and you can still apply the superposition theorem to calculate the final output at any node voltage or branch current. You can solve using superposition theorem. So next we discuss the Thevenin theorem, which is another theorem. The Thevenin theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH in series with a resistor RTH, where VTH is the open circuit voltage at the terminals, and RTH is the input or equivalent resistance at the terminals. When the independent sources are turned off. So, in Thevenin theorem, we have a linear two terminal circuit, we have two terminals and we want to solve this circuit using Thevenin theorem. So, it says in these two terminals we calculate the open circuit voltage replacing the other part of the circuit. Let us say we have a load where we want to calculate the Thevenin voltage and resistance. We replace the load by open circuit, find out the open circuit voltage, that is the VTH or the Thevenin voltage source. This voltage source is in series with RTH. RTH is the equivalent resistance of this entire network. We have this whole network keeping all the independent sources by their equivalent resistance. For example, voltage source we have that we short circuit, and we have current source that we should replace it by open circuit and calculate the total resistance, that is RTH. So, we can replace whole of this system or the circuit of this part by a VTH in series with RTH, that is the equivalent resistance of the circuit. So, this is what the Thevenin theorem is. Now, it is useful in the circuit analysis. This Thevenin theorem is useful the circuit analysis of power or battery systems where it will have effects on the adjoining part of the circuit. So this is what the Thevenin theorem is. Let's take one example to see how this Thevenin theorem is actually used. So let's find out the Thevenin equivalent circuit for this circuit given below. We have a voltage source, let's say this is 9 volt, where we have this resistance, this is 9 ohm, this is 3 ohm. Here we have this current source, this is 2 amp, this is 2 ohm. Here we have one more voltage source which is 3 volt. This resistance is 2 ohm and this voltage source is 10 volt. This resistance is 3 ohm and then we have one more voltage source which is this, and we want to calculate the Thevenin equivalent in these two terminals X and Y. So this is the circuit we want to consider. Let's say this node is node A, this node is, let's say, C, this node is, let's say, B, and this node is, let's say, D. Now we want to calculate how much is the Thevenin voltage and current and resistance values. So the solution is, we first apply KVL at loop A, C, D, B. In this loop, we want to apply the KVL. So we can write minus VAB plus I into R1. Let's say this is R1. Let's say this is R2. This is R3. This is R4. Plus 3 plus I R2 plus 10 equal to 0, and we know that VAB is 9 volt, which is given here. So we can put this value together and we can find out minus 9 plus 2I plus 3 plus 2I plus 10 is equal to 0. So 4 I is equal to -4, it means the value of I is -1 amp. So this is the value of current which is flowing in this loop I. So now we can calculate the drop in R2. That is 2 into -1, which comes out -2 volt. So this gives VC and D. This is 10 minus 2, which is 8 volt. So our open circuit voltage comes out VCD between the branch C and D plus 5 volt, that is 13 volt. So this is the open circuit voltage we have. Now let's find out the RTH. RTH is nothing but the 3 ohm is in series with 2 and 2 resistance, 2 plus 2, that comes out. So here RTH value is 4 ohm. It means this entire network, this complicated network, we can easily replace it with a VOC, the voltage source, in series with the RTH, which is 4 ohm. This point X, we have one resistance value RTH, which is 4 ohm, and a voltage source. This voltage source is 13 volt. So here we can see this very complicated system where we have 1 volt, 1 current source and 3 voltage source and so many resistances. The same network we can replace it with just 1 voltage source and 1 resistor if we calculate the Thevenin equivalent voltage source and the resistance of this network. So this network look very simple now, only 2 elements. So if we want to reduce a certain complex circuit, we can find a Thevenin equivalent of this circuit. So we can save a lot of components by making a Thevenin equivalent. So next we discuss the Norton theorem, which is very similar to the Thevenin theorem. Norton theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a current source IN in parallel with a resistor RN. IN is the short circuit current through the terminals and Rn is the input or equivalent resistance at the terminals when independent sources are turned off. So here in Norton theorem, this theorem is very similar to Thevenin theorem. In Norton theorem, we calculate the short circuit current instead of the open circuit voltage, just like Thevenin theorem. In Norton theorem, we short circuit both the terminals and find out the short circuit current between these two terminals. That is called IN, and then we calculate the RN, which is similar to the Thevenin theorem, that is now called Rn instead of Rth. Now the total equivalent of that circuit will be IN in parallel with the Rn. So instead of, for example, in Thevenin theorem, we have Vth in series with the Rth. In Norton theorem, we have IN in parallel with Rn. So this is the only difference. Other things are very similar. For example, we need to turn off all the independent sources in the circuit. Let's see one example for this Norton theorem. Let's find out the Norton equivalent of this circuit, which is this 5 ohm this is 10 volt this current is this resistance is 3 ohm. The current in this branch is considered I, and we have the value of this current source is 0.5 I, and this is 1 ohm. We need to find the current in 1 ohm resistor. So let's see this circuit. This circuit has one voltage source and one dependent current source. The value of this current source, for example, how much current it will generate, that depends on how much current is flowing in this 3 ohm resistor. By this symbol I, the current I is flowing in this 3 ohm. Whatever is the current in 3 ohm, the value of this current source will be half of that current. So, if for example 1 amp is flowing in 3 ohm, so half amp will be the value of this current source. This is the dependent current source we have in this example. Now, let us find out the current in the 1 ohm resistor, which is this, we can assume this as a load resistor. How much is the current using Norton theorem? So, let us find out how we calculate. So, first we remove 1 ohm resistor. If we remove this 1 ohm resistor, this current will become 0 because there is no path for the current to flow. Current cannot flow from here to here. It means this I will be 0. So, if there is no current flowing here, the value of this current source is 0.5 I, and I is 0. So, this current source will also disappear. There will be no current source exist which is 0.5 I because I is 0. So, our circuit is simplified very much. This gives us the open circuit voltage as 10 volt, because this branch does not exist and this branch does not exist. So, whatever is this 10 volt voltage source between the bottom and the top, that is the only voltage source. It gives V open circuit as 10 volt. Next, we short circuit the output terminal. If we short circuit the output terminal, the circuit diagram look like this. We have this 5 ohm, this 10 volt, this 3 ohm, and here we have this short circuit, and short circuit current will be flowing in this. This current source will become 0.5 times I short circuit, because this I short circuit is I. So, we can write now nodal analysis in this, and we can find out V minus 10 divided by 5, where I assume this node 1, plus 0.5 times I short circuit plus I short circuit is equal to 0, and here we have V is equal to 3 into I short circuit. This is the voltage at this node, which is V here. So this is short circuit multiplied by 3, which is the 3 ohm resistance here. So if we put this, then we can find out 3 times I short circuit minus 10 divided by 5 plus 1.5 I SC is equal to 0. So this gives us the short circuit current is equal to 0.95 amp. So this is the short circuit current, and similarly we can find out the R internal. This is V open circuit divided by I short circuit. This is 10 divided by 0.95. This comes out as 10.52 ohm. So R int value is this one. So we can replace the same network by a current source whose value is 0.95. This is in parallel with R int or R internal resistance. The value of this is 10.52 ohm. This whole network is now connected to our 1 ohm load resistance. So if this node is, let's say, X, this is Y, this node is X, and this node is Y. These are all connected. So here we can see we have a complicated system where we have a dependent current source and other voltage sources. That also we can solve it, and we can minimize it to a simple Norton equivalent current source in parallel with Norton equivalent resistance. So this is all Norton theorem. Now let's quickly discuss the maximum power transfer theorem. So maximum power transfer theorem says that maximum power is transferred to the load when the load resistance equals to the Thevenin resistance as seen from the load. So, maximum transfer theorem says we have a circuit which is delivering some power to the load. So, this power which is being transferred, this power will be maximum if the load resistance is equal to the internal resistance of the circuit. So, this internal resistance is nothing but the Thevenin resistance of the entire system. So, when the load becomes equal to the internal resistance of the system, then maximum power will be transferred from the source to the load. This is what the maximum power transfer theorem says. So, let us see how it look like. For example, we have this voltage source VTH and we have this RTH, which is the equivalent resistance of the entire circuit. This whole system, this can be a multiple element system. This is providing load, this power to this load RL. So, this power will be maximum if RL is equal to RTH. So, maximum power when RTH is equal to RL. So, the same thing we can see from the graph itself. For example, if we vary the load resistance RL here, this load resistance, let us say we vary from short circuit to an open circuit this side. Initially the power will be 0 and this will achieve a maximum value P max. This P max happens when RL value is equal to the RTH value, the internal resistance of the entire system, and both the side of this RTH the power is less. So, here we can see we have the load resistance which we need to tune it, because in many application we want to achieve a maximum power at the load, so that we can draw maximum power and we can transfer it or transmit it over the distance. So, we want to have maximum power at the load. How do we do it? We tune out the load so that the load resistance becomes equivalent to the internal impedance of the entire system. At that point, we can see the power is maximum, and this power decreases both the sides. Even if our load resistance is higher than internal impedance or lower than internal impedance, both the sides this power reduces. It achieves maximum at RTH, and at that point when RL is equal to RTH, half of the power is being burnt in the load and half of the power is being burnt in the internal resistance of the system. So, let us say the whole system is burning 1 watt of power at this point. So, maximum half watt will be delivered to the load, half watt power will be consumed in the internal circuit only. So, this is what maximum power transfer theorem says. So, this is very important theorem when we want to develop complex system and want to achieve maximum power at the load. We use this maximum power transfer theorem. So, we discussed some network theorems. These are nothing but the techniques based on KVL and KCL only, but we can directly apply them on the circuits to achieve at the output much faster than KVL and KCL. So, this is all for today. Thank you.